One thing I wanted to mention about this activity is that I have never presented reactions like this before for a class. This is really like a new exercise for me. You guys know that because in the past I've sometimes added too many arrows to for reactions that we don't have to show. Instead, what I typically will do is put at the top previously seen reactions, and then we just do a list, and I number them. And that's a downside of this, is that we don't have as much space to name them. So I'm going to try to write the names out so that we can see the names for these reactions as well. Because you guys saw this on the midterm exam. Sometimes I talk about descriptions of reactions. Yeah, you had that question that was like, step 1 is best described as acyl addition, EAS, reduction. No, I didn't do reduction because it was reductive. Or oxidative, right? So I'm going to try and name these as we go through them as well. But this should probably save us a ton of time from just doing a single list. Another downside of this, though, I'm a little bit limited on my carbon chains. So I don't want you to think that these reactions are limited to this position in a carbon chain. I want you to recognize that you can do these at a benzylic position. You can do them in a ring. You can do them in a lot of different ways. This is just an example. So by saving time here, I'm hoping that we have more time to do other examples as well. All right, so this was left blank for you to figure out what structure is on the left, what structure is on the right. But there are some interesting mirrors, like the alkyne is giving two different products. We know that alkynes can be hydrated to ketones or aldehydes, depending on the reagent. And then we have a secondary alcohol and a primary alcohol. That should have been the clue to you that on the right-hand side, we're hydrating the alkyne and oxidizing the alcohol to an aldehyde, a 3-carbon chain. And on the left, we're oxidizing the alcohol and hydrating the alkyne to a ketone. 3-carbon chain. So acetone or 2-propanone and propanal. Those are our two products. All right, reagents to do alkyne hydration. If I want this hydration to have this regiochemistry, hydrogen adds to the less substituted carbon, that's Markovnikov, I need to use oxymercuration. So I'm going to have mercury sulfate, HgSO4, with H2SO4 and H2O in addition. You might remember that with alkynes, we do oxymercuration reduction, and we actually use mercury acetate, and then water and acid, or just water, followed by a reductive step with sodium borohydride. This is just oxymercuration, no reductive step. And we're not using mercury acetate, we're using mercury sulfate and sulfuric acid. Here are alkyne hydration is anti-Markovnikov, and so we still need an anti-Markovnikov hydration reagent. This is first borane, followed by oxidation. Hydrogen peroxide with water and hydroxide. That is basic aqueous hydrogen peroxide. Familiar? I think we reviewed it in Unit 1 when we looked at all of our OCHEM 1 reactions. Now I can look at my oxidations. Oxidizing the secondary alcohol to the ketone, there are two reagents that I can use. Also, if this were allylic, there would be another reagent as well. But I can use PCC, a mild oxidizing agent, Or I can use chromic acid, a strong oxidizing agent. These will only oxidize to the ketone. There's only one hydrogen to remove. That's an oxidation of secondary alcohol. On the right-hand side, we've got oxidation of primary alcohol. What reagent can I use here? PCC. I cannot use chromic acid. Why not?
It makes a carboxylic acid.
Good. We're actually going to learn today that chromic acid will first oxidize a primary alcohol to an aldehyde, and then oxidize the aldehyde to a carboxylic acid, which means you can take an aldehyde with chromic acid and also make a carboxylic acid. What reaction did you guys predict coming down from the top? Did you want to answer that? Or you had a question?
Is it KMNO4?
KMNO4 would not be the right answer. No. It's close.
And use... is there a way to pause at that intermediate somehow with the CrO3?
Yes.
Pause the aldehyde?
Excuse me. You change it. Instead of chromic acid, you use pyridinium chlorochromate.
Can you... So...
No, if you have chromic acid, you cannot prevent the further oxidation of the aldehyde. Instead of KMNO4 is oxidative cleavage, but it's very similar to oxidative ozonolysis. It takes any hydrogens that are positioned on the alkene and it oxidizes them to a carboxylic acid. So I don't want KMNO4, and I don't want O3 with H2O2. What did you guys have here?
O3 with DMS.
Good. Reductive ozonolysis. O3, we could use DMS, or anybody else have a different reagent? Elemental zinc. Both of these are considered what type of reagent? Oxidizing agent or reducing agent? I hope not for reductive ozonolysis. These are both reducing agents. Think of zinc, which likes to become zinc 2+. Zinc has electrons to give away. It will reduce something else. DMS, rather than giving electrons to something else, DMS will take the oxygen on itself. In both of those ways, they prevent this hydrogen from being oxidized, which is what allows us to keep it as an aldehyde in the product. In OCHEM 1, I like to teach that the ozonolysis reactions, it's like stretching that CC double bond, sawing it in half, and placing an oxygen on either side. You get two carbonyls as a result.
Just alkene turns into a carbonyl and disappears? What, the propanol? Propane?
Propanal. So, on the left-hand side, I have a 1, 2, 3 carbon chain. The carbon of the alkene is the carbon of the carbonyl. 1, 2, 3, carbon of the carbonyl came from the carbon of the alkene. On the right-hand side, I've got this 1, 2, 3 carbon chain. 1, 2, 3 carbon chain. The carbon of the alkene is the carbon of the carbonyl.
So it turns into both.
Yes, and if these two R groups were connected, if this side looped back around and connected to the other side, you saw that alkene in half, and now you have, instead of a ring, a cyclic chain with 2 carbonyls. Maybe I can try to clarify that. Yeah?
Sorry, can I ask why this is reduction? Because I said oxidation, because I think of oxidation as being increasing the bonds to oxygen or electronegative atoms while like decreasing also hydrogen, and then like I think of reduction being the opposite, and so since this increases also oxygen,
Oh, there's no eraser. I heard all of what you said, and it's a great question.
Do you want me to go get you paper towel?
No, it's okay. I think I can wait until halfway through the class.
I can go now.
No, don't worry. So, I actually had, before I instituted any exam analysis assignments, I had students that were really upset at me in OCHEM 1 because I put ozonolysis on their exams and I didn't put it on their study guide. So they felt, oh, thank you.
Yep.
They felt that that was cheating. And I'm good for right now, but can I keep it until the end?
Yeah.
Thank you. They thought that was rude, that I didn't tell them to know ozonolysis products, when I actually said you don't need to know the ozonolysis mechanism. So I had to come up with like a way to help them earn points back, right? And so I said, write an essay on why it's called reductive ozonolysis and oxidative ozonolysis, despite the fact that both carbons become oxidized during the process, during both processes. So carbon to carbon, this carbon right here has an oxidation state of 0. And in the product, it has an oxidation state of +2. That is a loss of electrons. Oxidation is loss. So why is it called reductive ozonolysis? It's not being reduced at all. This carbon goes from -1 to 0. No, to +1. So they're both being oxidized. The answer here comes from reductive ozonolysis leaves the products more reduced than oxidative ozonolysis. By the way, I was just talking about how if these R groups were connected and you did oxidative cleavage, you'd get a linear chain. So that's O3 with DMS. But if I did this O3 with H2O2, aldehydes are not produced, which is why oxidative ozonolysis is not one of our reactions here. Ketones are produced, that's true. But aldehydes would be oxidized into ketones. In fact, I wanted to point out that I uploaded your learning objectives sheet for this unit. And we're not specifically going through this one, but I've got reductive ozonolysis and oxidative cleavage, ketones only, of alkenes. So you can do oxidative ozonolysis to make ketones, but you cannot do oxidative ozonolysis to make aldehydes. Yeah?
thank you.
You're welcome. Great question. So both are considered oxidative cleavage. They cleave a bond and oxidize. But within them, one is a reductive version of ozonolysis and one is a more oxidative version of ozonolysis. It's a great question. From the bottom, what functional group do I have in the bottom?
Alcohol.
It is a diol.
Oh.
Can we be more specific about the regiochemistry of the two alcohols? Good, vicinal diol. So what reagent did you guys put here to get the 3 carbon chains to split into the ketone and the aldehyde? Nobody got this one?
Could you just...
HIO4, periodic acid. So this is also oxidative cleavage. This we learned in OCHEM 2. This was in reactions with alcohols. But to separate this oxidative cleavage from this oxidative cleavage, we can call this cleavage of vicinal diols. clarify what conditions are necessary. Any questions there? Now, the other side, truthfully, maybe not clear enough. I think most of you probably understood what was being asked down here. We have benzylic alcohols and we have allylic alcohols. What can we do with those alcohols that share the same reagent to give us aldehydes and ketones? Yeah, MnO2. This will make benzylic alcohols that are secondary into ketones and benzylic alcohols that are primary into aldehydes. It's a selective reagent, but it's not strong. It's still mild. It's only going to oxidize one hydrogen from that carbon. And on the bottom, secondary allylic to ketones, primary allylic to aldehydes. Why is it we haven't seen tertiary alcohol being oxidized? We've seen secondary and primary.
Because it's not favored?
Not possible to oxidize a tertiary alcohol. Oh, actually, that's a tertiary alcohol.
Yeah.
And that is being oxidized by cleavage. And it's not just a tertiary alcohol, it's part of a vicinal diol. So it's unique in that respect. Oh,
Because of the other alcohol you can do it?
absolutely.
So you turn that into hydrogen, you can't do it?
That's correct.
What?
Absolutely. Okay, so up here, I saw a couple of other good answers. I wanted to show you acylation. On one hand, acylation to make an aldehyde, and on the other hand, acylation to make a ketone. However, there were some good points brought up about what reagents are feasible. So I'm actually going to show this a couple of different ways. If you wanted to make an aldehyde off of a benzene ring, you would need formal chloride with AlCl3. If you weren't going to use formal chloride, you could actually use what did we call this?
Anhydride?
Oh, but its name. It is an acid anhydride, but its name.
Oh. 1 second.
Formal chloride.
We
Form
form
formic anhydride. So Friedel-Crafts acylation, acylation. I don't think Friedel and Crafts get credit for the anhydride.
Did you give its common name in class?
We talked about one carbon carbonyls, and we looked at all of the functional groups. Formal chloride, formic anhydride, formic acid,
Oh, the
formaldehyde.
bottom one.
Yeah, formic anhydride. We did talk about it. In fact, I even Googled it up for you and I showed it to you on the board. All right, so for the bottom one, same thing. We could look at a lot of different structures here. So I'm just going to give an example. This will just be a 3-carbon acid chloride, or it can be a 3-carbon anhydride. But again, I'm just picking 3 carbons for the sake of it. It could have also been a benzene ring. It could have been a cyclohexane ring. It could have been a tert-butyl group. It could have been anything that you would like to imagine, so long as the chemistry doesn't interfere with the acylation. All right, there's one last way to make aldehydes and ketones. It's a specific aldehyde. We haven't seen it anywhere on here. Most aldehydes are the same. It's a primary carbon. So it's got some carbon chain connected to it. But there's one aldehyde that is unique from all the other aldehydes. It's not a primary aldehyde carbon. How can I make formaldehyde? Now that I'm thinking about it, there might be a few right answers here.
Dang it. Methanol. Oh,
Yeah?
PCC on methanol.
Good.
Okay.
PCC, oxidizing methanol. Oxidative cleavage.
3 over zinc or something.
Good. Reductive ozonolysis of ethylene.
Doesn't it make 2?
It would make 2 equivalences of formaldehyde. Absolutely. Anything else? I think we can think of one more. It's going to have to be another cleavage reaction. No, actually, alkynes only go through oxidative cleavage to carboxylic acids. Only to acids.
Would the oxygen be like in between 2 carbons? Could you have one with oxygen is carbon, oxygen, carbon, and break it there?
Mm-mm. You're talking about an ether,
Yes.
but that's not going to oxidize it to an aldehyde, to a carbonyl. Ethane 1,2-diol. Also known as it's got a common name. And I'm gonna kick myself when I see it. Glycol. You guys know glycol?
Ethylene glycol?
Ethylene glycol? I don't know. Whatever.
Just go down.
I thought it was a biochemistry word.
Okay.
What reagent would I need with ethylene glycol to make 2 forms of formaldehyde? It's on the board, by the way. The reagent is on the board. We're just reiterating different ways we can use these reagents. Periodic acid. HiO4, because that is what functional group, Jacob? Vicinal diol. All right.
Is that useful? Well, not useful. Is that applicable on quizzes and tests?
To know how to form formaldehyde, definitely. Definitely.
It's not natural.
You can form. What is natural?
You could find it on an expedition.
I don't know. Never been on an expedition where I found formaldehyde. All right. Those are all of the ways we've previously seen how to form aldehydes and ketones. We're now moving on to new ways to form aldehydes and ketones. So this is on your sheet. We're going to look at this 6-lined graph that all shares the same reaction. We're looking at a new reduction reaction. We're looking at reduction with diol, pronounced like eyeball, said diol. Can you guess at what diol is an acronym for? Notice that L is lowercase. That's AL. Aluminum is in there.
Barium? Boron?
Boron is not in there.
Barium.
Barium is not in there.
Butte.
Yes, it is a butyl.
Deionized butyl.
Not deionized butyl aluminum. Di, IB, isobutyl. Isopropyl is the 3-carbon peace sign. the 3-carbon Y. Isobutyl has 4 carbons plus the little Y at the end. This is diisobutyl aluminum hydride. Aluminum hydride, ring any bells? LAH has aluminum hydride. This is a mild cousin of LAH. Do you remember how many hydrogens LAH had attached to it?
2.
No, LAH has more than 2. Lithium has what charge in lithium aluminum hydride?
Sorry, there's 4.
Yeah, lithium is plus, so the aluminum hydride must be a minus. Aluminum takes on 3 bonds, neutral, 4 bonds with a negative charge. So LiAlH4. How many hydrogens attached here?
1.
Just 1. So LAH is a great reagent to use in excess because there's a ton of hydrogens attached and it will donate all of them. How many hydrogens will this donate? Just 1. And remember, LAH needs to be followed with an aqueous workup. It's the aqueous workup where the alcohols become protonated. Same thing here. Nothing is going to happen after the first step. So Dibol can only reduce once. No matter what functional group is there, it can only add 1 hydrogen, and then we need an aqueous workup to change things. So all of these different reagents, there's 6 of them, they will all react Dibol followed by aqueous workup to give us this aldehyde. That's the aldehyde that we're going to be aiming for. Okay, remember, we could have picked any carbon chain on the other side. I could have put a benzene ring there. I could have put an alkene ring. There's a lot of correct answers. I'm just keeping it short and simple. You guys okay with that? I can use Dibol to reduce an acid chloride. Do you remember what acid chlorides got reduced to last time? Acid chlorides are reduced with NaBH4 and LAH to alcohols, primary alcohols. This is a partial reduction. I substitute chlorine for hydrogen, but I keep the carbonyl. That's the key piece here. I can also partially reduce acid anhydrides. It is important to recognize here that I also get a byproduct of a carboxylic acid. Only one of those carbonyls is reacted with, the other carbonyl is not. I can also partially reduce a carboxylic acid. Do you remember what acid anhydrides were reduced to before? Two primary alcohols with LAH, 1 primary alcohol, and a carboxylic acid with NaBH4. Do you remember what carboxylic acids used to be reduced to? A primary alcohol with LAH and no reaction with NaBH4. Dibol is changing that for us. It's allowing us to do a partial reduction. In fact, if you wanted to say that, instead of reduction with Dibol, you could say partial reduction with Dibol. After this, we see esters get reduced. This does give us a byproduct of ROH which comes from that ester linkage. This should be clarifying a pattern that you're seeing. The carbonyl oxygen never leaves, but it's whatever group is connected to the carbonyl that does leave. So let's backtrack a little bit. Can you guess a byproduct of reducing the acid chloride? No, probably not HCl. But chloride. I guess during the aqueous workup, the Cl- might get protonated to form HCl, but the chloride is lost. What about during reduction of the carboxylic acid? An equivalence of hydroxide or water if you're considering after the aqueous workup. What comes next for our last two? Amide. I'm just going to abbreviate that as NR2, but R can be H, or there could be a combination of N and R groups. And of course, here we get an amine byproduct. And then lastly, the nitrile. Now we learned the 2-carbon name for all of these, correct? Acetyl chloride, acetic anhydride, acetic acid, acetate, some sort of alkyl acetate, acetamide, and the nitrile was acetonitrile, CH3CN. And this also produces an amine byproduct, but actually it's NH3 that is kicked off. So not just an amine, the amine, ammonia.
Where's the oxygen coming from?
The aqueous workup. That's a great question. The nitrile is the only one that doesn't already have a carbonyl oxygen. So then where in the world is that carbonyl oxygen coming from? The carbonyl oxygen of the aldehyde is coming from the aqueous workup.
Are you making NH2?
Somewhere along the way there's NH2.
Would it be NH2 instead of NH3?
No, that would be NH2 minus.
Oh, one of the hydrogens.
But because there's an aqueous workup, an acid workup, I guess I should give this to you guys. You guys had the right idea. This would be HCl after the aqueous workup. This would be H2O. You wouldn't have a carboxylic acid without the aqueous workup. You wouldn't have an alcohol without the aqueous workup. If you're considering before the aqueous workup, you'd have to say chloride, carboxylate, hydroxide, alkoxide, amide, and amide. Confusingly, amide is the conjugate base and also the functional group. All right, I want to talk to you guys a little bit about what's happening inside of here. These are not mechanisms I'm going to ask you to know, but they are going to relate to mechanisms we talk about in a bit. So I want to show you guys the intermediates of the diball reduction.
Show the mechanism?
Yeah. I'm going to abbreviate diball, and rather than drawing out that isobutyl chain. But I am highlighting the ALH bond in writing diball here. Who owns the electrons in the ALH bond? Aluminum. Hydride. What does hydride mean?
Negative charge.
H minus. Exactly. Which is not a negatively charged proton because protons only have positive charges.
Does it also make hydrogen gas? The cyanide?
No. Nitrile.
Nitrile?
Hydrogen owns these electrons. It takes them away from the aluminum and it binds to our carbonyl carbon. This is called a tetrahedral intermediate. You can tell because of the way it looks. We have this diball sitting with a positive charge. Now, this is not a mechanism I'm going to ask you to show, but many people would show you that oxygen binds to the aluminum. That is perfectly reasonable. However, there is a step here. This does not entirely like sitting as a tetrahedral intermediate. If it can reform the carbonyl, it will. But in order to reform the carbonyl, this tetravalent carbon will need to get rid of one of its groups. The Cl. We would say the Cl is a good leaving group. And what do you know? An aldehyde. Now you need to work it up and get rid of all that aluminum junk and isolate your organic product. That's what the aqueous workup is for. But it's in that one step where you're done. Okay, now imagine that you had done this with lithium aluminum hydride instead. So we're just imagining here that it was this compound that donated its H. And now this compound, AlH3, has another hydrogen to give. And I should have maybe drawn it over here so we can see its relevance a little bit better. What's going to happen to the aldehyde? It will get reduced. The hydride will attack the carbonyl. What good leaving group then would come off? Nothing. You have O minus, 2 hydrogens, and your carbon chain.
2 hydrogens?
Yeah, if this reacts further, this would attack and break this open. And now you have a primary alkoxide. Now you do an aqueous workup and you get an alcohol. So reduction of the acid chloride, even with NADH4 or LAH, they have enough equivalences of hydride to fully reduce the acid chloride, reduce to an aldehyde, and then further reduce the aldehyde to an alcohol. Diball stops that reduction. So NADH4 and LAH reduce aldehyde intermediate. Diball only reduces once. That's the benefit, is that you pause it at that intermediate.
That's the final product?
Well, acid chloride to aldehyde, yes, that's the final
With
product.
LAH?
With LAH, you still have the aqueous workup. So you protonate the alkoxide into an alcohol. All right, so I want to talk about some of these other intermediates. The acid anhydride. tetrahedral intermediate, what's it going to kick off? A carboxylate. It's actually the conjugate base of a carboxylic acid. This will form my aldehyde plus a carboxylate. Didn't we say the carboxylic acid can also be reduced by Diebol? So why isn't this reduced? Two reasons. The Diebol is consumed. The second reason, this is not a carboxylic acid. It's actually less electrophilic. It has extra electron density around it. This is harder to reduce than a carboxylic acid. Let's talk about the carboxylic acid. What will this kick off? Now maybe you're thinking back to OChem 1, where I taught you that CO bonds are bad leaving groups. You shouldn't break a CO bond. We actually saw back in Unit 3 with ethers that you can break CO bonds, like in ethers, in really strong acidic conditions. So maybe you're not convinced that this will reform a carbonyl and kick off the hydroxide. It's very likely that it will, but I'll hear you out. What if this intermediate waits around until the acid workup? Then we get this intermediate, where O- gets protonated, and now I have a geminal diol. I'm going to show you guys in a little bit that geminal diols in acid form aldehydes and ketones. Specifically, this is a primary geminal diol, so it will react in acid to form a primary carbonyl, the aldehyde. I'm going to skip the, well, actually, I guess I won't skip the ester. I'm going to skip showing so much of this. The ester has a very similar combination. This O- can kick off OR. If it doesn't, perhaps there's an equilibrium issue, it can wait until it gets protonated. What would you call this functional group? It's probably not one you've seen before. I like to call it a gem etherol. If this is a gem diol, because they're, why do we call it gem or geminal? The star sign twins, Gemini. Geminal means twins. Geminal diol. So this I like to call a gem etherol because it's both an ether and an alcohol in the same carbon. There is actually a name given to this. It's called a hemiacetal. What does hemi mean? Half, like a hemisphere. So what's an acetal? That's a functional group we'll talk about in a little bit. Same thing with the amide. Now, amides are truly hard to kick off. The CN bond really is stronger than the CO bond. So again, we get this into a protonated state. Oops, and R2. Once again, we could call it like a gem amine all. There is another functional group that's kind of involved here, and so I like to think of this as a hemiamine, but it doesn't, I don't know, it's a little bit confusing. if you know what an imine is, it's a CN double bond. And this doesn't look anything like a CN double bond, so it's confusing to say why this is halfway to it. But it's characteristic of the hemiacetal in some of the reactions we're going to do later. And then lastly, the nitrile. This one I think I'd like to show a little bit more. When the diball attacks, it attacks the nitrile carbon, which breaks the CN triple bond. And this is called an imide.
Imide?
Kind of like an amide is a negatively charged amine. This is an imine, a CN double bond, and it's also negatively charged. It's an imide ion. And we're going to learn how imides react in acidic conditions to form aldehydes as well. This is why I bring all of this up. These are bonding patterns that we're going to see a lot in this section. So I want you guys to be familiar with how this set of reactions has intermediates that we're actually going to see over and over. All right, why don't we take a 5-minute break so you guys can get up, move around, and really move around, get the air flowing in here because it's hot again. I think it's winter. I think they turned on the heat, and that's why these rooms have been getting hot. So get the blood flowing, and we'll come back in to look at the rest of our reactions.
Do you want these windows open?
Pretty sure they don't.
Would you?
Would I what?
Open them.
If they did. I'm pretty sure they don't.
Good to know.
Okay. What did we learn?
Good instinct of when to open windows. Nice. Oh. You park over there?
Yeah, my usual spot.
Oh yeah, I do.
Better than my usual spot, actually.
Because you're closer to the tree?
Yeah.
Great tree.
Closer to the classroom.
And the tree?
It's closer to the tree.
Like, if you could park where the handicap stop is, or by that tree, which one would you do?
By that tree, I guess. I think it's closer. It's all about proximity. How quickly can I get away from you? Oh!
Publicly?
Public.
Did you say publicly? Can I get away from you?
No, how quickly?
Oh.
How publicly can I get away from you? Well, then I would just shout. What are you good on? I need to start erasing.
All the black and orange can go.
Okay, did you get this one down?
No.
The nitrile to the imide.
No, I didn't. Ah, I'll start going. Would the dival and the chlorine make a crystal?
Well, they would be aqueous soluble.
What is that?
Means that
Is it
they
salt?
Mhm.
Makes it salt?
No. They're yes. The chlorine would very likely bond to the dibol. but that the fact that it's aqueous soluble means it wouldn't precipitate out. It would stay dissolved.
Yeah, but when you dry it, you get a crystal.
When you dry what? This would go into the aqueous waste.
No one wants diball chloride.
Not that I know of.
How
I'll
could we?
be honest, Killian, I've never touched diball with my hands.
You've not. You mean like you've seen it?
Never seen it. Never touched it with my eyes either. There you go. No.
In December, I am in and so it's my brother's wedding.
Congrats.
Thank you. And I was trying to
Probably a
make
month long.
Yes.
Yeah.
And I was trying to make them so it's not falling on my iron.
Yeah.
But then it will be.
Sure. So when are you hoping to leave?
So I'm gonna be here until the 7th.
Okay.
So I think I would have to study myself 2 weeks prior.
Well, the last week of class is review.
Yes.
That's useful. You would be missing just review. So if you wanted to take it on the 7th, that would also be like you have to have the Unit 3 test done by then as well. Because I'm going to be grading for the Unit 5 test. I'm going to be grading the Unit 5 test here. So you're going to want to take the Unit 5 test as quick as you can. So that you can also take the midterm right after it. But here's the deal. I also want you to be able to do your best on it. Would it be feasible for you to do a proctored exam while you're away sometime during this week to give you more time to get ready? Pakistan is what time difference? Like 12 hours? Yeah, okay. So if we met at like 8 a.m. my time, we'd be meeting at 8 p.m. your time. Would you be comfortable after you get adjusted to jet lag? Would you be comfortable taking a 2-hour exam from 8 to 10 p.m. in Pakistan?
Have you seen the organ exhibit? Yes.
The natural history museum?
Yeah,
In and out, in and out, in and out.
sure.
Never stable.
Yeah.
It's,
Don't remember that.
no, it is,
Well, I don't-
I'm not going with November. They're like, okay, we can do December.
I've seen it twice.
Mm,
I wanna go back.
yeah, it's more doable. But it's still
It
hard.
was amazing, and then yeah, all the
Oh wait.
Well, I want you to be able to enjoy as much of it as possible. Because that's huge. My partner is also trying to go to Libya for his brother's wedding next summer,
Oh my gosh.
which is
In summer,
yeah,
exhibition.
yeah. So I understand. Like it's a big thing. You want to be there for all of it. So I wouldn't like for you to have to push it back. And I want to see if it's possible for us to do it over there so that you can leave and still have time to study and be prepared.
I've been making everything. I've been studying every day.
Good. Good. So why don't we keep talking about it?
Okay.
And if worse comes to worse, and we just feel safer doing this, then we'll just do this, and we'll take it on the. You're leaving on the 7th.
Okay. Me too.
And if that doesn't work, something comes up, then we'll figure something out about the Wi-Fi situation.
Okay. I think I might have a stable Wi-Fi.
And you know, like we can,
It's so slow there.
yeah,
It's there,
yeah,
but it's just so slow.
then we can discuss what options we can consider. All right.
So I just wanted you to be aware.
Thank you for bringing it up.
Yes, it wasn't done until like recently.
I bet.
I was like, no,
Don't get married.
no, they really don't. You can't keep pushing it back. I'm like,
Listen, they gotta support their sister who's in college.
I know.
All right, Killian, get the nitrile before I need to erase it.
Okay. Can You leave the bottom half of that one. This one.
Can for a little bit. You're saying just all the intermediates?
Yep. What was the point of saying the LAH and NABH4 reduce the intermediate?
That's to remind you, an acid chloride will get fully reduced with our other reducing agents. That's the usefulness of Diebol. All right. Our last new production of aldehydes and ketones is hydrolysis. And you guys can see from the learning objectives, I maybe should have made this a list, a numbered list as well. Instead, I left it as a separated list. We're hydrolyzing a number of different functional groups. Many of these are going to be new functional groups, so I'm going to introduce them a little bit more clearly as well. This one, what we have here is a 7-lined list. Yeah, 3, 6, 7. So quite honestly, I'm not even sure how to summarize all of these at once because they're not all in the same category, but they're predominantly oxygen and nitrogen-based groups. All right, so 7 lines. 1, 2, 3, 4, 5, 6, 7. And our reagents here, H2O and H3O+. Acid catalyzed hydrolysis, which I want to keep in mind. That's basically the second step of Diebol reduction. H3O+, aqueous workup. That's what's going on here. So I was drawing your attention to a lot of the intermediates here are very similar to the functional groups we're starting with here. And so by forming these intermediates, you also are just doing these reactions. The reason that I'm bringing these reactions up now is because we're going to learn how to make all of these functional groups from aldehydes and ketones as well. So at the top of our list, we have the gem diol. Again, geminal, meaning twins, as opposed to vicinal, meaning in the vicinity of. Are my twins good? Thank you. Variation of one of these groups. Change one of the OHs to OR. I'm sorry, I have a mistake. I meant to actually have a CH3 group on the left and R on the right. And I wanted to clarify that all R's can be H or R, which is to say it can be a carbon chain or a hydrogen. Because the product we're forming here can either be an aldehyde or a ketone. These are not selective to just aldehydes or ketones. These were selective to hydrogens. Sorry. These were selective to aldehydes. But if we have any of these more generic functional groups, and they're not just the intermediate of our acyl reduction, these can be aldehydes or ketones. So, same problem here, CH3 on one side, R on the other. Correct me if I'm wrong. This does not need to be a CH3, correct? Correct. Could be a benzene ring. Could be a long carbon chain. We're just keeping it short for simplicity's sake. Functional group here, hemiacetal. All right, finally, I can show you what the acetal is. We could call this a gem diether, but instead they call it an acetal. Do you guys remember what acete means? Two carbon carbonyl. A 2-carbon carbonyl group. And al tells us what as a suffix? Aldehyde. So very likely, the aldehyde version of this compound is what gave us the acetal, where acetaldehyde formed a gem diether. Listen, I don't know. They are weird with how they name things. But the acetal is the gem diether. And IUPAC is trying to revive the name of the ketone analog, which is, they're trying to call it a ketal. It still has al in it, which indicates aldehyde. And then it starts with ket, which indicates ketone. No idea what they're trying to go for there. So, in general, the scientific community accepts that acetals include the gem diether of ketones and aldehydes. IUPAC is trying to push that aldehyde is the gem diether of aldehydes. Sorry, acetal is the gem diether of aldehydes. Ketal is the gem diether of ketones. Nobody's accepting it. And IUPAC should just get over it. Those are our oxygen-based groups. Gemdiols, hemiacetals, and acetals. Can you see a little bit more clearly now why it's called a hemiacetal? It's like halfway to an acetal. There's not 2 OR groups, there's just one. We're actually going to see the mechanism for these reactions, and we will see that the hemiacetal is formed halfway to the production of the acetal. Another side fact, some people call this acetyl. And I refuse to pronounce it acetyl because that's like they're saying YL. We already have that for things like acetyl chloride. Or biochemist people, acetylcholine. So I try not to pronounce it as acetyl, and I try to pronounce it as acetal. All right, now we get into our nitrogen-based groups. The first group, this is an oxime. I don't know where the name really came from here. Anyways, the next one is called a hydrazone.
Do you mean to put R on the end there?
No, it should be, it's almost always NH2.
Oh, well, oxime.
On oxy, this is NOH.
So, 2 methyls. You mean to make 2 methyls?
Oh, I appreciate that, yes. This is R. This is R. Sorry, I misunderstood what you were saying. It is true, though, that sometimes hydrazones have other groups coming off of it, not just NH2. But it's pretty common for hydrazones to be NH2. I'm not sure if you want to be specific about that. You can just put NR2 there. And unless otherwise stated, R generally can be hydrogen as well. Then we have the imine. The imine is the carbon-nitrogen double bond. And I'm going to put R here as well, but of course it could be H. And then our last group is the enamine. You'll notice on the enamine, that the CH3 group that has been constant in all of these other structures is now a carbon-carbon double bond. It's a CH2 group. The reason being, the nitrogen groups that is attached is NR2. That nitrogen group can't take a double bond. All of our nitrogen groups are like nitrogen derivatives of an aldehyde or ketone. Instead of an oxygen, there's a nitrogen present. But the enamine can't take a double bond, like the imine, the hydrazone, the oxime. So instead, the double bond is structurally isomerized. The double bond is between the carbons rather than between carbon and nitrogen. Which of these functional groups looks the closest to the intermediate of the dibol reduction with the nitrile? The imine. Which means when the imide forms, and then you do aqueous workup on the imide, you protonate the nitrogen and you form an imine. And we know that imines get hydrolyzed in acidic conditions back to aldehydes or ketones. So if you reduce a nitrile with dibol, you will form an imine intermediate, which then hydrolyzes to the aldehyde. If you reduce an amide, this does not look exactly like any of our functional groups, but we are going to see how this is an intermediate in the hydrolysis of the imine or the enamine. The gem etherol is the hemiacetal, and we said that can be hydrolyzed. We have the gem diol as well. All of the intermediates that we saw in the dibol reduction are analog functional groups to things that can be hydrolyzed to aldehydes and ketones. So I'm reiterating that we are seeing a lot of reactions that are kind of overlapping with each other. They're all very similar. All right, now we are flipping the page. We're moving into reactions with aldehydes and ketones. I don't know that we have as much time for all of you guys to solve these on your own, but I think we do have enough time to get some brainstorms from you guys. What reactions have you seen this semester? There were no reactions before this semester. I'm going to hide it. Had it on the screen. What reactions have you seen before this semester? During this semester with aldehydes and ketones. Do you want one of these?
Wow.
Okay. By the way, Maddie, you still got to send me that list.
Oh, yeah, so sorry.
I was going to email you.
Oxidation.
Reduction of, or reduction with.
There's the multiple between, I think.
True.
The NaCH4.
Do you know what I wanted to have here, I think, is an R group, so that we can say R is hydrogen or a carbon chain, so that we can look at this in terms of aldehydes and ketones. You said reduction with what again? Sorry. Reduction with NaBH4. So first, NaBH4, second, H3O+, and what will that give us? Alcohol. If R is a hydrogen, then this alcohol is a primary hydrogen, a primary alcohol. If R is a carbon chain, then this is a secondary alcohol. So we're getting down to an aldehyde or a ketone. What else? Reduction with LAH, was that the only reduction you saw? Okay. I'm gonna skip a spot because there's another similar one here that I want to come back to. But we did see the hydrazine reduction. H2NNH2 with potassium hydroxide, and what did that give us? Alkane functionality. All right, now analogous to the hydrazine, there was another reagent that we used. Oh, and by the way, I called it hydrazine reduction, but its legal name is the Wolff-Kishner reduction. Hydrazine, by the way, sounds a lot like hydrazone, and there's a nitrogen-nitrogen bond in hydrazone, and there's an N-N bond in hydrazine. Hydrazine is a reagent that we'll use to make hydrazones. What was the other reagent? Do you remember? Yeah, zinc, mercury, and hydrochloric acid. I can't remember if I gave you the mercury last time, but oftentimes it's written as zinc mercury. And this does the same thing down to an alkane. Whose name was this given? That was this semester. Clemensen, although I like to call it the metal acid reduction. Clemensen reduction or the metal acid reduction. All right, there was another reduction that also gave us an alcohol. LAH. First LAH, second H3O+. This has no discrepancy between aldehydes and ketones. NABH4 and LAH both work. All right, now there were a couple of other reductive reactions, but they're more broadly considered acyl addition. Acyl addition with, what did we do acyl addition with a lot? Organometallics. So we can write this as R, well, first we have to put RM. You could put RMGBr or RMGX, or you could put RLI. I'm going to put RM because what does M stand for? Metal. Followed by an aqueous workup. Okay, maybe a little bit confusingly, I've now got two R groups attached. This was acyl addition, and I'm going to remind that we can do RMGX, RLI, but we can't do the cuprate, R2CULI. Do you remember the other acyl addition reagent that we used? I think we talked about it very shortly, if at all.
Grub?
Not grubs. Same one.
Oh, sorry.
Grignard and organolithium, interchangeable. Not an alkene, because actually the alkene could be attached here as the R group. Hydrogenation? No, we won't do hydrogenation of it. We could, but we won't do it. Kayla, what was yours? Not the cuprates. The cuprates won't attack the carbonyl. This was with cyanide. And this gave us the cyanohydrin. So it's also acyl addition. But instead of using an organometallic, we're using cyanide.
Where's the other H? Hydrocyanide?
We can show it as this, thank you. First, cyanide, second, aqueous workup to get the alcohol back. Which of those reactions feels the least familiar? Yeah, the cyanohydrin addition. Now it's time for new reactions. I'm going to turn this back on so you guys can see. I tried to be as clear as possible, although maybe I could have been a little bit more clear. I put Wolff-Kishner and Clemmensen reduction, but I put them in the same line. And then I have LAH and NADH4 as separate ones. So I'm not sure why I should have maybe been clear in every different reagent had a different line, but I kind of added them together. And then you can see I also have the acyl addition to alcohol, acyl addition to cyanohydrin. Acyl addition to alcohol is where I'm saying they organometallic, giving us an alcohol. All right, your new reactions. Sorry, I forgot what this one looked like. 7 arms. 7 arms. What else had 7? No, for real. What else had 7 things that we've talked about? Our hydrolysis. So we're going to flip this on its head. We said that all of these different functional groups can be hydrolyzed to an aldehyde or ketone. And now we're going to say how an aldehyde or ketone can react to form all of these different things. Ready? To the diol. We have 2 different ways. And you can actually see we're not necessarily going in order. We're looking at 6 and 7 here. No, we're looking at 5, 6, and 7. The diol can be made by water and acid, or by hydroxide and water. You can hydrolyze the aldehyde or ketone in either basic conditions or acidic conditions. We'll be looking at those mechanisms on Thursday.
Is the or this way or this way?
Hydroxide and water, or water and... I guess it wouldn't matter. It wouldn't matter. It makes the exact same combination. To the hemiacetal, I'll need acid. Ooh, look at that acid. What is that acid? A proton, yeah. Do you know how to isolate a proton to put it in your reaction? It's very hard. Specifically, I'm not saying H3O+. And the reason is, water being present here will drive this process backwards. So if I had H3O+, all of the product that I get has a chance of hydrolyzing back. So I'm adding H+, and good choices for H+ are tosylic acid, TSOH. You really don't need to know what the TS is, but I know some of you are just really inquisitive. I bet you guys could even make that. Start with benzene, methylate it, and then tosylate that. And you got tosylic acid, toluene sulfonic acid. Para-toluene sulfonic acid. The reason that this is better than H3O+, this is organic. H3O+ is aqueous base, which means it allows for hydrolysis. TSOH is organic. You don't need water to bring it with. Another good option, acetic acid.
Don't have to dissolve in water?
These will dissolve in water.
Don't they have to?
No, they don't have to dissolve in water. You can add glacial acetic acid, which is like less than 1% water by volume. Some of these will pull water out of the air, by the way. It's true.
They're liquids without water?
Ever heard of gasoline?
That's
It's a
not what
liquid
I'm saying.
without water. No, I'm sorry. I get what you're saying. These are liquid at room temperature without having water, necessarily. Or if they're not, and I might be wrong about toxic acid, acetic acid is definitely liquid without water. Toxic acid, maybe I'm wrong, but it will dissolve in polar organic solvents as well. These are the best ones. These are the ones I would recommend, but you can also use H+. I will say the conjugate base of tosylate is very easy, TSO-. The conjugate base of acetate is very easy, ACO-. Do you know what the conjugate base of H+ is? Nothing is the conjugate base of H+. So when you have a reaction that involves an acid in one step and then the conjugate base in the next, when you use H+, you have nothing to show as the conjugate base, and it just gets confusing. So I would recommend these options as H+, but we're going to abbreviate it as H+. H+ with alcohol. I'm going to be specific here. One equivalence. One equivalence of ROH to the aldehyde or ketone. That is acyl addition. Plain and simple. That is adding an equivalence of alcohol across the aldehyde or ketone. Great.
Make hydrogen gas?
No.
Where does
Acid catalyzed alcohol addition.
Where does the other hydrogen go?
The H from the alcohol goes to the oxygen of the carbonyl.
And the acid is a catalyst.
Acid catalyzed. Yep. Acid catalyzed acyl addition.
Just to make sure I read it down correctly, the ROH applies to if you also use a TSOH for ACOH reaction, right? Or is it only H+?
H plus can be TSOH or ACOH. And then you also need an alcohol.
The alcohol. Okay.
The alcohol could be methanol, could be glycol, could be propylene glycol. We'll talk about that one too in a little bit. It could be ethanol. It could be phenol. It could be a lot of different things. Yep. But you need an alcohol. Next, H plus and two equivalences of alcohol to give us what functional group?
Would it kick off the arc?
We already made the gem-diol, and we just made the hemiacetal with one equivalence of alcohol. This gives us the acetal. Where do you think the oxygen of the carbonyl went? Is the oxygen of the carbonyl one of those OR groups? No, those O's in the OR groups came from the ROH, the alcohols. We have actually just kicked off a molecule of water because we have lost two H's from the two equivalences of alcohol, and we have lost an O from the carbonyl, H2O. This is a dehydration, a condensation reaction, if you will.
What is the byproduct is water?
Water. Yep. Now, in this step, you will sometimes see an additional reagent added, and that additional reagent is MS. I'm going to elaborate a little bit more on what MS is. Maybe I didn't spell sieves right. A molecular sieve is something that pulls water out of a solution. This is a material. It's these tiny little balls. These balls are like smaller than BBs in a BB gun, or a little bit larger than like a grain of salt. And inside of this sphere is this like network of overlapping pores, and those pores have a size of about 15 angstroms. "15 angstroms is fairly small. An atom, on average, is a few angstroms wide, which means a molecule would be a dozen or more, at minimum, angstroms wide. So the smallest molecules can fit inside of here. What's a small molecule? H2 is a small molecule, not super common in our reactions here. H2O is a small molecule. Methanol, not as small. Toslic acid, nowhere near as small. So molecular sieves essentially soak up H2O.
Any other small liquids?
No, this is why we use it. It will soak up H2O, which prevents hydrolysis. In the reactions we're looking at, hydrolysis is equilibrium. Hydrolysis is the reverse reaction. I need to make sure that I do not have equilibrium. I want to make as much of the product as possible. Le Chatelier's principle says that if you are going to form water as a byproduct, that increasing the amount of that product will shift the reaction backwards. So, add molecular sieves, pull out the water as it forms, and you can actually continue to drive the reaction to produce more product. It's not just helping the equilibrium, it's pushing it in the direction you want. That sounded a little weird. It's not just preventing equilibrium from going backwards, it's helping equilibrium go forward. All right, those are my oxygen-based groups. Now for the nitrogen-based groups. These are all acid catalyzed. H+ with hydroxylamine. Any idea why we would call that reagent hydroxylamine? You could write it two different ways, by the way. I like to indicate that the N and O are bonded to each other explicitly by putting H2NOH, but you could also write NH2OH. Why would you call it hydroxylamine? Yeah, it's pretty straightforward. One of the only things they did right in organic chemistry. And what functional group is this going to form? The oxime, yeah. CN double bond. With OH coming off. What's a byproduct formed here? H2O. The two H's of the amine are gone, and the O of the carbonyl is gone. So what would help in keeping as much product as possible? molecular sieves would be really useful here. Here's the deal. I'm not going to mark you off if you don't put molecular sieves on the reagents. I'm more interested that you have the chemicals down. And it's pretty easy to digest what chemicals are needed. If you have hydroxylamine, you need to remove the 2 hydrogens from N and the carbonyl, and you are left with the oxime. If you have the oxime, you need to add 2 hydrogens to the N and replace the carbonyl oxygen. So I want you to get used to looking at these patterns. What is bonded and what needs to be added. After the hydroxylamine, let's talk about forming the hydrazone. H+, molecular sieves are helpful. And what reagent would you have to make the hydrazone? I'll give a hint. It's on the board. H2N, NR2, or NH2. Hydrazine would work here. H2N, NH2. It would give us a hydrazone specifically where the 2 R groups are both hydrogens if we used hydrazine. What did we do? We cleaved the CN double bond. We gave 2 hydrogens back and the O back to a carbonyl, and we got hydrazone. So these are inverses of each other. And you're identifying this pattern now of what you need to use to make. I'm sorry, I think my sentence died halfway through I was saying it. You're learning how to identify what reagent you need to make that functional group. This also produces a byproduct of water. That's why the molecular sieves can be so useful here. To the imine. You'll notice that the imine has an R group, which means it needs specifically H+ with H2NR. It must have 2 hydrogens because those 2 hydrogens will then be kicked off of the nitrogen and will leave as water. Again, a great spot to have molecular sieves. Anytime water is the byproduct, molecular sieves is useful. I'm going to point out this pattern again. NR, N, NR2, N, OH, they all needed a reagent with NH2 so that the 2 hydrogens could be kicked out with water. Now for the last one, the enamine, where specifically 2 of the R groups stay. Once again, H+, molecular sieves is useful, and we need NHR2. 2 H's do not go back to the N, because one of the H's must go back to the alkene. We've been kicking out a molecule of water all this way, and for the most part, we've been kicking that molecule of water off with 2 hydrogens from the nitrogen group. But now my nitrogen does not have 2 hydrogens, so where will the second hydrogen come from? The second hydrogen for water comes from the alkene, comes from the adjacent carbon, adjacent to the carbonyl. That means enamines can't form in very specific functional groups. If your carbonyl has no hydrogens on the sides of it, then your carbonyl cannot form an enamine. You need to have at least one hydrogen adjacent to form the enamine. All right. Taking you guys past. Thank you for your time. On Thursday, we'll look at mechanisms and try to practice these problems. Have a good night.
Do we need to finish that blue thing up?
Do we need to finish the blue thing?
Do you mean to?
This?
Yeah.
That was just to show you can write hydroxylamine two different ways. Whichever way makes the most sense to you.
What's the orange one?